Hey there, hi there, ho there. Welcome to Unit 6, Igneous Rocks and Volcanoes. We're now tiptoeing into the rock cycle. So for the most part, we spent the past few units looking at the tectonic cycle. Now we're tiptoeing into the rock cycle. So we'll start that conversation with igneous rocks. It's kind of a natural progression going from plate tectonic cycle to the rock cycle. So we'll start there. We'll take this unit to talk about igneous rocks and volcanoes. Unit 7 will be sediments and sedimentary rocks, which we get over here. And then as we continue through the rock cycle, Unit 8 will be metamorphism and metamorphic rocks. Now, once we're in the rock cycle, we really could go any which way. It's just usually the story we tell starts with igneous rocks, then sedimentary, then metamorphic. So that's how it's set up. As a refresher, this was just briefly touched on in last unit. We're talking about minerals and a brief introduction to rocks. These are all igneous rocks. So all igneous rocks start off as some melted, molten material. How it cools, how fast or how slow, will determine the type of igneous rock that's created. But first, let's talk about that melted stuff. So let's talk about molten rock, because that's where it starts. So here you have a volcano. You have some molten rock below the Earth's surface. That's known as magma. When magma is defined as molten rock below Earth's surface. Lava is molten rock above Earth's surface. So it's two different names for the exact same material. If a volcano is erupting and we have magma through here, as soon as it erupts to Earth's surface, magma, lava. Two different names for kind of the same stuff. So it just depends on where it's at. Both are for molten rock, magma below Earth's surface, lava above Earth's surface. So where does this molten liquid magma come from? You might be asking yourself. Well, that's a good question. So if we're looking at the layers of Earth, we have the solid inner core, the liquid outer core, the mostly solid mantle, and the solid crust. So again, where could liquid hot magma come from? Where could liquid hot magma come from? Well, as you probably guessed, not the outer core. Haha, tricked you. Yes, the outer core is liquid. Molten rock is liquid, but they're not the same stuff. So where does molten rock come from? Where does this liquid, molten, hot, melted rock come from? It comes from just between the mantle and the crust. That's where it comes from. So, due to mantle convection, in plate tectonics, you'll get some small magma zones, areas where the crustal or upper mantle material will melt. Because remember, mantle is mostly solid, crust is solid. But due to plate tectonics, some stuff going on, you'll get little spots that rock will begin to melt at. And this is where magma comes from. It comes nowhere near from the liquid outer core. It's a common misconception, and I just said it to kind of trick you. So yeah, so magma for the most part comes from the upper mantle or crust area. So how does it form? Well, it forms again from the partial melting of the upper mantle or crust. So initially, as mantle material moves upward due to mantle convection, remember it's still mostly solid, or if mantle material has water added to it, it starts to melt a little bit. And that's what gives us that molten rock, magma. So as the molten rock, magma, begins to rise, it's less dense than the other material around it. Since it's a liquid, it'll begin to rise. Gas molecules in the magma start to come out of solution and form bubbles. And as bubbles rise, they expand. So it has to deal with a decrease in pressure as this material is rising up through the upper parts of the mantle and crust. Eventually, the pressure from all these bubbles kind of built into this magma is stronger than the surrounding solid rock itself, and the surrounding solid rock is under pressure itself. It is fractured due to all this pressure, allowing the magma to get to the surface. So there's a couple of ways in which magma melts. There's a couple of ways in which the upper mantle and/or crust melts to form magma. The first is called what's known as more of a dry melt. and it's a reduction in pressure. Due to, let me see if I can write, chemistry, the ideal gas law is PV equals nRT, if you remember a little chemistry. So this equal sign, meaning whatever happens on this side, happens on this side. So as the pressure decreases, so does, make sure I get this correct, so does the melting temperature of the material. Yes, so as the pressure decreases, so does the melting pressure of the material. Meaning, no, I can't erase here. So meaning, as this material rises up through the upper parts of the mantle and the crust, the pressure begins to decrease. As such, let me get out of here now. So when this mantle material starts to push upward into the areas formerly occupied by the crust due to crustal thinning, cracks in the crust, or divergent boundaries, the pressure begins to decrease. So in a dry melt, we're not adding water. It's the big difference between dry melt and what we're going to see next. So the pressure drops because, again, where for some reason the mantle material is pushing upward into areas formerly occupied by the crust due to crustal thinning, like what happened below Arizona to help our volcanics, cracks in the crust, or divergent boundaries. Again, you're giving a pathway for mantle material to work its way up. As it does, the pressure drops, therefore the melting temperature of the mineral also drops, meaning it's much easier to melt that material now. You're now melting that mantle material. An example where change in pressure changes temperature, if you boil water at sea level, where air pressure is the highest, it boils at 212 degrees Fahrenheit. You go up to the top of the mountain, top of a mountain somewhere, up in the Rocky Mountains somewhere, where air pressure is lower, water boils at a lower temperature, 200 degrees Fahrenheit, or even lower. So this illustrates that a change in pressure can change the temperature at which materials will change state, from a solid to a liquid, or in this case, from a liquid to a gas if you're boiling water. Therefore, in a dry melt, at whether crustal thinning, cracks in the crust, or divergent boundaries, is that if there's a path for that solid mantle material to get closer to Earth's surface, that causes the pressure to decrease, which causes the melting temperature of the material to decrease, and the mantle material can begin to melt. So it's a dry melt, because we're not adding any water to get this process going. Where we do add water is flux melting, which is known as a wet melt. As typically at convergent boundaries, as that subducting plate at the convergent boundary is creeping its way down, it's bringing with it some water as well as carbon dioxide. Whether that's gaseous or locked into the rock material, it's bringing that material into the mantle at the subduction zone. This water and gaseous carbon dioxide, they move through the crystal mush of a developing magma body and, again, chemically lower, in this case, silica's melting point. That's a class of minerals. Quartz is in that. So it, again, by adding water, you're lowering the mineral's melting point by, in this case, several hundred degrees. Therefore, once this process is started, you're now melting material because water is lowering the melting point, causing more material to start melting. When it does, the pockets of all the liquid magma start to incorporate more and more silica from the surrounding rock, as like quartz and olivine and a number of different minerals, creating a more stickier magma. The more silica-based minerals, like quartz, the most common mineral in the Earth's crust, the more minerals like that we add into a magma, the more stickier it becomes. And that then begins to dictate the type of magma, which will dictate the type of volcanoes created, which will dictate the type of explosivity of the volcano, which will dictate the type of rocks that are made. There's a lot of dictations. So there's two kind of ways in which the mantle material can melt. So when we do start to melt that material, we get different types of magma due to different types of melting and due to different ratios of the stuff that we're melting, if that makes any sense. When we're looking at melted material from the upper mantle, we're creating typically something called basaltic magma, coming from a little bit deeper down. It has a little bit different chemistry if we're talking about melted material kind of from in between the upper mantle and the crust, at one of these subduction zones. We get a lot of wet melting. The upper mantle, this basaltic magma, more typified by dry melt. This subduction zone area where you might get maybe a little bit of basaltic, but definitely andesitic magma is more typified by a wet melt. And then if you're melting kind of upper crustal material, again, mostly dry melt, you're tiptoeing into the realm of rhyolitic magma. So what we're going to do, we're going to pause here. When we come back, excuse me, when we come back, we're going to talk about those different types of magma. Basaltic magma, andesitic magma, rhyolitic magma. Distinguishes the differences between those three and kind of what those three different types of magma can do. So let's pause here. I'll see you back here in just a second.